Access to field vibration data is not always available. In such cases, the only option currently available is the use of generic PSD functions to generate steady-state, constant RMS random vibrations. This approach does not produce realistic vibrations, and it has been shown to have significant shortcomings. A software module called the Vehicle Trip Synthesizer was developed especially to overcome this limitation. The module can be accessed from the SVS system as is shown here. The Vehicle Trip Synthesizer module relies on the fact that if a vehicle is treated as a deterministic mechanical system, and if some information about the excitation process is known, then it is possible to make reasonably accurate predictions of a system's response. The main principle behind the Vehicle Trip Synthesizer is that it combines various imported ingredients to compute estimates of the average PSD and the RMS distribution function. These main ingredients are, firstly, a model that describes the spectral characteristics or spectral density of the surface elevation profile of pavements. These are shown on the graph on the right of the screen. These spectral models are used by the International Standard Organization and have been found to be an accurate representation of road profiles, sometimes known as road roughness. It is interesting to note that the shape of a spectral function doesn't change. Instead, the RMS level changes with road roughness. The second ingredient is the transmissibility of a particular vehicle or vehicle type. There exists a number of numerical models that can be used to compute the transmissibility. These include heavy vehicles with air ride suspension or leaf spring suspensions, among others. The transmissibility function is displayed on the graph located at top left of the screen. The third and last ingredient needed to complete the process is a schedule or table describing the variation in road roughness, the corresponding vehicle speed, as well as the corresponding duration. This is called the trip profile, and an example of it is shown on the graph located at bottom left of the screen. Now I will demonstrate how to configure these ingredients to define a particular test schedule. I will start by selecting a suitable vehicle type. This is done by using an existing model or creating a new vehicle model. As for the statistical vibration synthesizer software, this data is administered with Microsoft Excel. We can select a model by scrolling down the list, which contains various models such as that from Todd and Kulakowski from Penn State University. Note that the transmissibility graph is automatically updated as a new numerical model is selected. Or a steel suspended heavy vehicle model from Seaborn of Cambridge University. The zoom utility can be used to adjust the scales. There are a significant number of such vehicle quarter car models available in the public domain. They characterize a broad range of vehicle types, including small delivery vans to heavy vehicles with various suspension types. As mentioned previously, vehicle models can be created or edited by accessing the relevant Excel worksheets as follows. Note that the models used here are quarter car models that are needed to simulate vertical vibrations. It is of course possible to use more complex models if the data is available. The parameters required to define a vehicle model are the sprung mass, suspension stiffness and damping, as well as the second degree of freedom parameters, which comprise the axle mass, tire stiffness and damping. Note that the SVS software will only read data from the first two columns of a spreadsheet. Once these parameters are defined, the transmissibility function is automatically calculated and plotted. Now a trip profile needs to be defined. For this, we need information or estimates on the types of roads in terms of roughness that are likely to be encountered. Using the ISO classification method, letters are used to classify road roughness, with A defining a very smooth road and up to H for very rough terrain. The trip schedule is managed with Microsoft Excel. The vehicle speed and duration of the road sections need to be defined as well. A trip profile library can be easily edited directly from Excel as shown in this example. Here I have decided to simply delete the last entry. After the worksheet is saved, the library needs to be reopened to show the updated trip profile. Note that the order or sequence in which the trip profile is defined is irrelevant, as is the overall duration of a trip profile. This information is only used to compute the overall mean PSD and RMS distribution. The system is now configured to compute the mean response PSD and the distribution of the RMS levels of a particular vehicle traveling on a variety of road types at predetermined speeds and for specific durations. Before this is done, we need to define the frequency range over which the vehicle response will be computed. This is done by adjusting the values in the text windows located on top of a screen. In this case, we select 1 Hz and 120 Hz as our frequency bandwidth. The frequency resolution is also adjusted. And the RMS histogram bin size can also be adjusted. The synthesize button is then pressed to compute the vehicle response, and it updates the graphs showing the average PSD and RMS distribution. It is important to understand that the shape of a response PSD is influenced by the vehicle dynamic characteristics alone. The road roughness and vehicle speed affect the RMS levels of the vibration response, shown here as a statistical distribution. We can easily change the bin width of the RMS distribution histogram. This demonstration has shown how a simple quarter-car vehicle model can be combined with estimates of road roughness and vehicle speeds to produce estimates of a vehicle response PSD as well as the distribution of a vehicle response RMS. These can now be stored as target functions to be used by the SVS system for reproducing non-stationary random vibrations. This is done by using the Export to SVS Libraries tool. This creates new worksheets in the PSD and RMS distribution Excel libraries containing information about the target PSD and target RMS distribution. We can now return to the main statistical vibration synthesizer software module. Because the libraries were modified, we need to refresh the libraries by using the Reopen Current Libraries facility. We can now select the newly created RMS distribution and target PSD. First, I select the target RMS distribution, which is automatically updated on the RMS distribution graph. Then I select the target PSD. Note that the new worksheets are named automatically as a combination of a vehicle type and the trip profile names. It is interesting to note how the combinations of RMS levels we have chosen results in a significantly non-Gaussian distribution for the vibrations. If we look at the PDF on the bottom right of the screen, we can see that the target kurtosis is 5.2 compared with the equivalent Gaussian of 3. This demonstration has shown how, in the absence of field vibration data, far more realistic vibration tests can be created using the vehicle trip synthesizer module.